So this is a ESP32 based wireless oscilloscope. It's got a pretty rudimentary analog front end consisting of one amplifier up here for small signals, and yeah, that's about it. Additionally, right now it's currently using the ESP32's inbuilt analog to digital converter. The plan was to use an external SPI based one, but due to time constraints and footprint issues, namely ordered the wrong one for the board size, that didn't end up happening. However, that's very easy to add in terms of SPI communication. You know how to do that from up here, and really that's just reading a value from an SPI chip is very straightforward. So this is test startup is just connected to the analog discovery and its function generator output, sorry. So this is the simple part. Let's take a look at the software. So software is written in Java. It's a lot of lines, and we'll jump into the computer now. Okay, in terms of software, we'll start off on the ESP32 side. It's a culmination of a lot of stuff around and code on my part, but anyway, just going to press the reset button on the board right now, and we'll take a look at the serial monitor. Now, this is not required at all in terms of plotting, or in terms of data communication, sorry. This is purely output only, just done for debug purposes. You can connect it to any random 5-volt USB source and it'll work totally fine if it had the requisite network connection. Here we go. Let's just connect to Wi-Fi. And okay, some more debug output, and it is connected. So now we're going to open up the Java code to interface with it. Okay, so this is the controller software. It discovers it by scanning all of the 8-bit, the range from 0 to 255 in the last part of an IPv4 address, and sees if it's open on port 2812 if it's listening. If it is, it tries to initiate connection, which is what this data down here is about. But anyway, we've got a connection. We'll select it, and we've got a lovely big window here. So just make it nice and large. A few issues. The UI programming is not my strong suit, but it does work. Okay, now I can actually see it's beginning to actually look like wave. Does it match up with what we've got here? So a 500 Hertz sine wave. Let's maybe slow that down a bit so it's just really obvious. 50 Hertz, yeah. And let's clear the trigger yet again. It's reset itself. We'll download the sample data, and we'll redraw it. So there we go. Oh, that is really lovely. And oh, can't see it, but it goes from 1.4 up here to 0.4, and that's pretty much matches here. So that's just an issue with the amplifier. Okay, so here we've got the trigger at 0.8 volts, so it triggers nicely off of here. Yeah, but now let's just give a demonstration of it in action. So change this up to something much higher, so 1.8 for example. We'll update the trigger level. You can see here it's been updated. We'll clear that. At 10,000 samples per second and a 4,000 point memory, it must have filled up by now, so we'll download the sample data. Now this won't be correct by any stretch of the imagination. Looking, it'll be all jumbled up in order. You can see here, while it's continuous, sorry, it looks correct, and then see here to here, that's about half the sample memory, and here to here is the other half, so it wraps around to, you know, just pass a few pointers for the trigger points and then have it rearranged later. A 1.8 volt trigger level. We'll go over here, change the input amplitude to 1 volt, so it's 2 volts peak to peak. It's larger. Trigger has instantly set. Let's download some sample data. Bada bing, bada bang, bada boom. redraw a graph. Okay, so now I can see the nice new waveform. It's triggered on this.